Alrighty, let's lock in, everybody. Get your notebook, get a pen, pencil, whatever you want to write with. This is math from the void. Math coming at you from basically out of nowhere. You have no idea where this is coming from. You just hear a voice that's talking about calculus and showing you what you need to know to be successful on the AP Calculus exam. Here we're taking a look at a problem from 1998. It's BC2. It does have a lot of elements of an AB problem, so the material is not exclusive to those who understand Calc BC. Even many Calculus AB students could and should strive to solve these types of problems. I'll remind you that the BC exam is largely identical to the AB exam. Probably something like 60 to 70% of it are exactly the same questions that the students who are going to be taking the AB exam will be having on theirs. So because this was so blurry, I wanted to type things out just to make sure that you can read the question clearly. The function is sort of hard to read otherwise. The function is 2x times e to the 2x. Okay, that's the function. And I've typed out what these parts are basically asking of you. Part A, find the limit as x goes to negative infinity and the limit as x goes to positive infinity of the function. So let's start there. Let's imagine what happens as x goes to negative infinity. The limit as x goes to negative infinity of 2x e to the 2x. Well, this is basically going to tell us the same thing as the limit as x goes to infinity of negative 2x e to the negative 2x, which is going to be equal to the limit as x goes to infinity of negative 2x over e to the 2x. Now you should know that e grows much faster than a linear expression. So this is going to a very large value of infinity, in a sense faster than this is going to infinity. Because this is going to infinity over infinity, it's technically an indeterminate form, and you could use L'Hopital's rule. So this is going to be equal to the limit as x goes to infinity of the derivative of the top, not the quotient rule, but the top and bottom derivatives separately, over 2 e to the 2x. And now it's pretty clear to see that the denominator is getting much larger, and so this is just going to 0. Now what about the limit as x goes to positive infinity? Well, I think that's clear that this is just going to infinity. There's no negative involved, so this is just going to be like a really, really big number times e to a really big number, and that's just going to give us a really big number. So part A is done. Very simple. Part B, it says to find the absolute minimum value. Absolute minimum. Now there's no interval given, so we don't have to consider an interval. We just have to consider critical points. It says justify your answer. So we're going to do that by taking a derivative. The derivative of this is going to require the product rule. Take the derivative of the first. I like to do this. And what that reminds me is to take a derivative of the first, that's the double bars, and leave the second thing the same. Plus I leave the first thing the same, and the double bars tell me to take a derivative of the second part, that's going to be 2e to the 2x. So if I factor out 2e to the 2x from the derivative, I'm going to be left with 1 plus 2x. And when you want to find maximums and minimums, you take a derivative, and then you set them equal to 0 or undefined. Now, fortunately, we're working with e here, so something you should remember is that e is never going to be 0. In fact, it's always going to be greater than 0. But this could be 0. 1 plus 2x could equal 0. That happens when x is negative 1/2. So the only critical point that we have here is when x equals negative 1/2. If we put this on a chart, like I said, e to any power is never going to give us a negative. It's never going to give us 0, so it's always going to give us positive. However, when x is negative 1/2, we do get a 0 on the second factor there. Anything less than negative 1/2 is going to give us a negative. Anything greater is going to give us a positive. So that tells us that the derivative is negative, and then the derivative is positive, making this a minimum point. There's our minimum. In fact, we know the graph is going downwards and then going upwards in some way. So let's find if they're asking us what the minimum value is. Yeah, they're asking us what is the absolute minimum value. Not where does it happen, but what is it? So we're going to need to plug this into the original function and see what the minimum value is. F of negative 1/2. That's going to be 2 times negative 1/2 times e to the 2 times negative 1/2 power. These cancel and gives us negative 1 times e to the negative 1, which is negative 1 over e. That is our minimum value. The justification is since f prime, I guess I can say it this way, since f of x is decreasing until this point, and then it's increasing afterwards, and it's increasing forever afterwards because the derivative is always positive afterwards. That's enough justification to say, well, this has to be the lowest point then. If it's going down, 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 no matter how it's going down, and then it eventually hits a minimum, and now it's going up, 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 doesn't matter how it's going up, this has to be the largest, the smallest value, the minimum value. Okay, so we've justified that. Part C says to find the range. Now this is really interesting because it's the lowest point and we have a sketch here. Part C is going to let us know where our range is going to be. If it's constantly going up and then it's constantly going down to the left of it, the question is, does it ever go any lower? No, it doesn't go any lower. The lowest it can go is negative 1 over e. What's the highest that it can go? Well, if you remember from part A, we found those limits. This says that as x gets really big, the function goes really big to infinity, which means there's virtually no maximum value. There's no limiting finite limit. And this is our range. It doesn't quite have a sketch of graph, but I do want to emphasize that because the limit as x goes to negative infinity was 0, that does mean that the graph is going to look something like this. Something possibly like that. It might make a concave up shape. Might do something like that. Not too sure. But I know that at negative 1/2 we reach our minimum value of negative 1 over e. And if you use a calculator for it, that's fine. I don't know if this was a calculator problem, but it can certainly be done without a calculator. So let's assume that it's a non-calculator problem. And then it's going to respect this boundary and never quite cross the 0 there. Okay, part D says to consider the family of functions bx e to the bx. So b is just some number. This time we had 2. In this problem, we were working with 2x e to the 2x, but it's having us consider bx e to the bx, where b is just some non-zero number. It could be negative, could be positive. They want us to show that the absolute minimum value is the same. So let's confirm that. Let's take a derivative. If y equals some bx, it's just a number. Don't be scared, guys. It's just some number. Then its derivative, similar to how we did the derivative for part b, this is going to be product rule. So derivative of the first part, leave the second part the same, plus leave the first part, take a derivative of the second part. So bx times b e to the bx. That seems about right. Now if we factor out b e to the bx, then we're left with 1 plus bx. We want to find critical points, which means this equals 0. But remember, this is never equal to 0. This e expression is never equal to 0, whereas this expression is equal to 0, specifically when x equals negative 1 over b. Now to find the minimum value, we have to plug that in. So we'll say y equals negative 1 over b times bx. Sorry, bx is going to be b times negative 1 over b. There we go, that's better. Times e to the b times negative 1 over b x. And so we're going to get the same kind of cancellation that happened with the 2. We're going to get negative 1 times e to the negative 1, which is in fact negative 1 over e. So no matter what the b value is, our minimum will always be negative 1 over e. No matter the b value, as long as it's not equal to 0. And that is a full-fledged AP Calculus problem from 1998 on the BC exam. Continue watching this series and we'll discuss other types of functions from free response tests. See you next time in the void.